All right. So now we're talking, this has, heat capacity is only kind of loosely related to what we've been talking about. Okay, heat capacity is somewhat related to, climate and things like that, but it's also very much related to physical properties of materials that we talked about way back in the 4th day of this semester. Okay, right before we did the properties of compounds lab where you had to identify the unknowns. Okay, this is also a physical property of materials. Okay, in the same way that solubility, state, melting point, and all that kind of stuff is, specific heat capacity is specific to each material. All right, so every material has a different specific heat capacity. Now, what we mean by specific heat capacity is how much energy do you have to expose something to in order to change its temperature? Okay, as you've probably noticed that some things, if you heat them just a little bit, they get hot really fast. Other things, you can heat them and heat them and heat them, and they don't seem to change temperature for a very long time. Okay, for example, if you compare, let's say like a pan, okay, that you would use to cook with, versus the water you might put in it. Okay, if you just put a pan on the stove, and don't do this because it'll wrecks the pan. Okay, if you just put a pan on the stove and turn the stove on, okay, does the pan get hot in a hurry? Yeah. Pans are made out of metal. Metals generally have very low specific heat capacities. And what that means is they don't require very much energy to change their temperature. They get hot fast. Okay? Now, you fill that pot with water. Does it take a long time for the water to get hot? Like comparatively, quite a bit longer. Okay? Water has a very high heat capacity. That means it can absorb a lot of heat without changing its temperature very much. Okay? Everyone follow me there? Now, that is why proximity to an ocean is a major factor affecting climate. Okay, this is how it's tied in. Okay, specific heat capacity of water is very high. So, if you are near the ocean can store a lot of energy, and as it's transferring that energy to the air, its temperature doesn't change very much because it can hold so much energy. The air, comparatively, has a very low heat capacity. And so as a result, the energy coming to it from the water can raise its temperature quite a bit by comparison. Okay, you guys follow me there? Right, so that's why being close to the ocean can make you have a much more mild climate. The ocean is what we call a big heat sink. It can hold heat, okay, and it doesn't change its temperature very much. All right. Okay, so heat capacity then, okay, is the amount of heat required to raise the temperature of an object. Okay, so notice this heat capacity does not have the word specific in front of it. Okay, heat capacity talks about an object. Is an object made of possibly many materials? Yeah. Okay, if we're talking about an object, we could be saying like, let's say your coat, okay? Well, your coat would be made of, the liner, the fill, the zipper, all that stuff. It's all made of different materials, okay? So if we want to talk about just heating up your coat by 1 degree Celsius, we have to talk about the whole thing, okay? It's kind of an average of all the parts, okay? So we're talking about an object, okay? And the amount that we raise the temperature by is always by 1 degree Celsius. So the amount of heat required to raise the temperature of an object by 1 degree Celsius is heat capacity. The difference between heat capacity and specific heat capacity is this. For specific heat capacity, we're talking about a specific substance and a specified mass, 1 gram. All right, so we're back to chemistry where we do things small. Okay, everything is in grams for this. All right, so the amount of heat for specific heat capacity, it's the amount of heat required to raise the temperature of 1 gram of a substance. Now it's only one material. Okay, by 1 degree Celsius. Okay, everybody follow me on the difference here. Right, so heat capacity, we could be talking about a very big, heavy object like a truck. Okay. Whereas when we're talking about specific heat capacity, we're saying this material and only 1 gram of it. Okay. All right, so the specific heat capacity of a substance is a physical property, just like all the ones we talked about back in chemistry, and it is always the same for any amount of that substance. All right. Now, the formula that we use to calculate the amount of energy, okay, that would be E, required, or heat required to raise the temperature of something, okay, is done by doing this, multiplying the mass of the material by the specific heat capacity. That's what C stands for, capacity, okay, multiplied by delta T. What does delta stand for? Change, right. And what's the big T? Temperature. All right. So mass times specific heat times temperature. Right. That's going to give us energy in joules. Now let's just check our units here. What's the mass going to be measured in? Grams. Okay, so we're going to have grams. Okay, multiplied by specific heat capacity. Now, the units for specific heat capacity are joules per gram degree Celsius. Okay, so I'm taking grams, I'm multiplying it by joules per gram degree Celsius, and then I'm multiplying by degrees Celsius. So, grams cancels, degrees Celsius cancels, and I'm left with joules. Is that the units for energy? Okay, then I'm good. Now, is this formula going to be really, really easy to manipulate? Okay, if everything is multiplied together in that formula, if I want to solve for something, what do I do with the other things? Divide them away. If I want to solve for mass, I divide by C times delta T. If I want to solve for delta T, I divide by M times C. Okay, pretty easy formula to use. All right, so manipulation in algebra will not be a problem for any of you on this. Okay, it's a super easy formula to manipulate. All right, everybody with me there? Okay, so the things we really need to remember. Okay, what everything in this formula means, and how we tie this, the specific heat capacity, into that proximity to oceans factor affecting climate. Okay, that's the other thing we really need to remember there, is how that ties into factors affecting climate. All right, so I'm going to go over here some examples, just like I always do. Whenever we have problem solving or a new formula, I go over how to solve some examples to do with that formula. All right, so for example number 1, just write this one down quickly and then we'll go through it. How much heat, or energy, thermal energy in this case, is needed to raise the temperature of 150 grams of water, and the specific heat capacity of water is 4.2 joules per gram degree Celsius. Okay, from 5 degrees to 85 degrees Celsius. So in a question like this, again, write down your givens. You're going to get a mark for it. Okay, so we've got mass, 150 grams. Okay, we've got specific heat capacity, 4.2 joules per gram degree Celsius. So what that means is, if I have 1 gram of water, which is 1 milliliter, that's not very much. Okay, it would take 4.2 joules of energy to heat that much water by 1 degree Celsius. Okay, that is a very big heat capacity. Right? It may not look like it, it's only 4.2, but imagine 1 gram of water, okay, it's 1 milliliter. I mean, you guys have an idea how big 1 milliliter is. Like, it's just a small, tiny drop of water, really. Okay, so it takes 4.2 joules of energy to heat that by only 1 degree Celsius. That's why it takes so long to boil a pot of water. Okay, it's a lot more than 1 milliliter, and okay, you've got 4.2 joules for every degree Celsius and every gram of water in there. Okay, and then our temperature change, delta T, is how much? Goes from 5 to 85, so that's how many degrees? Hannah? 80, yeah, okay, good. All right, so there's my delta T. So all I have to do then is plug those numbers in. Okay, the math of that's going to be really easy. I don't have to manipulate. So 150 grams times 4.2 times delta T, okay, which is going to be 80 degrees. Come here, you. All right, so 150, okay, times 4.2 times 80. Okay, 50,400 joules. Is that a lot? It is. That's a lot. Okay, you would probably not eat that much food energy in a week. Well, unless you were having McRottens every day or something, then you might, but okay. All right. That makes sense? So 50,400 joules. Was it 50, or was it 8? 2004. Okay, good. All right. Okay, write this one down. Give it a try. All right, so for this one here, okay, our givens are mass, 100 grams, okay, the energy, 4,200 joules, okay, and we're told the temperature change from 12 degrees Celsius to 62 degrees Celsius, so our temperature change is 50 degrees Celsius. All right, they want me to find out what material it's made out of. What's the only thing from that formula I don't have right now? Specific heat capacity. And it is specific to a certain material. So if I find what C is, will I be able to match it up to a material on that table I just gave you? Okay, that's how you would figure it out. Okay, if we solve for C, we can match C up with the specific heat capacities on our table. All right, so that's what we got to do. We got E equals mc delta T. I want to solve for C, so I divide both sides by m delta T. Okay, and plug in my numbers. 4,200 joules divided by 100 times 50. Now, when you're plugging this into your calculator, that's got to be in brackets. Otherwise, your calculator will go 4,200 divided by 100 and then multiply by 50, which is not the same thing. Okay? All right. So 4,200, okay, divided by 100 times 50. Missed a 0. All right, so 0.084, okay, is the specific heat capacity that we're given there. Okay, and I missed a 0 again, didn't I? Yeah, so it should be 0.84, which is, for this stuff, I think it's copper, right? No, it's glass. Okay, so this material is made out of glass. Okay, what are the units for this 0.84? Joules per gram degree Celsius. Okay. Okay, is that one making sense to everybody? Okay. All right, I'm going to do another one here, make you think a little bit on this one. This is about as hard as they could get. Okay, what's the final temperature? Okay, not the change in temperature. What's the final temperature of a 185 gram block of iron initially at 7 degrees Celsius if it's heated with 200 joules of energy? All right, so those are my givens. Mass, specific heat, and energy. What can I find with those three things? I can find, which part of the formula don't I have? The change in temperature, right, delta T. If I find that, and I know what the initial temperature is, can I find the final temperature? Yeah. Okay, so that's what I'm going to start with. Okay, E equals mc delta t, and I'm going to solve for delta t by dividing both sides by m times c. All right, so we'll have our 200, okay, divided by 185 times 0.46. Okay, so 200 divided by 185 times 0.46. All right, so the temperature change is 2.35 degrees Celsius. Is that going up or down? Up. It says I'm heating it, right? I'm heating it up, so it's going to go up. So if my initial temperature was 7 degrees, my final temperature is going to be, so plus 7, okay, is 9.35 degrees Celsius. That's as hard as they get. Okay? I think you guys can handle that though, right? The answer to that is yes, you can. Whoop, 2.35. Okay, plus our initial temperature gives us 9.35 degrees Celsius as our final temperature. Okay, everybody good with that? Then you would subtract, yeah. Okay, all right. You got about 3-4 minutes. I want you to do a couple of the questions on that worksheet before class ends. We'll spend a little bit more time at the beginning of class tomorrow working on this, but not much because it's pretty easy. Okay, then we're going to move on to latent heat. Okay, we're making good time, guys. We might actually get one extra day, okay, of final exam review. I'm not going to change the unit exam. That's set. Okay, but we might actually get a day of final exam review before the unit exam even. Right now, we're moving along pretty quickly. We might get that. I'm not promising. We might get it. Okay.